just briefly introduce Dr. Sylvain Ho comes from Australia. He's a senior researcher in the university. He was doing the postdoc in Princeton for 2 years, and then he moved to Australia. And he made a demo in Bellevue a few years ago on the visible light positioning system. So his research is more in channel theory, information theoretical security, visible light communication and positioning systems, data communication and recording, data storage systems, and finally biometric security system as well. And he's presenting a paper in ISIT recently, where he came to visit us as well. So I will let Wai talk about it.
Okay, thanks Kelvin, and thanks everyone for coming to today's presentation. So today I will talk about the channel estimation and the visible light communications. And before I start, I will tell you a little bit about the work we have done for indoor positioning in our book. So I suppose everyone knows GPS. So GPS is very useful. For example, it helped me to come here from the metro station. I was wondering, okay, in this point there are multiple roads coming from the circle. So which road I should take? GPS is very useful. However, for example, in this building, we cannot use GPS because the signal from the satellite cannot penetrate walls into our mobile phone, for example. Then we need to have some other solutions for indoor positioning. But maybe you may wonder, okay, for building it is not so big comparing with the whole Paris, for example. Then why do we need an indoor positioning system? So indoor positioning system, of course, it can offer some other applications, very different from GPS. For example, in hospitals, there are some expensive equipment. So in the, for example, some operations, so these equipments may be shared in different wards. So they are expensive and they are portable. So sometimes we may want to locate them to find out where they are, because sometimes they may be misplaced. And also, during the outbreak of transmissible disease, for example, in around 2002, the outbreak of SARS, so we wanted to check the location of the nurse, doctor, and patients at that time in a hospital, so that we can find out whether certain doctor may have interacted with certain patients, and later on we found that this patient has been infected by some serious disease. Then we may need to quarantine the doctor or nurse because they may be infected as well. We don't want them to further propagate the disease. So the location information is useful in hospital for these applications. And of course, you may have seen that location information can also help us in a store. Maybe we want to find something in the supermarket. The supermarket is very big. And also it can help us to promote some product. For example, maybe we go to a supermarket, we want to make spaghettis. Then we can use our smartphone if it provides the location information. Then it can tell me, okay, where I can buy the spaghetti, where I can find the sauce, cheese, etc., all the ingredients. And also it can make the shopping experience more interesting. Maybe there are some coupons, some interactive experience we can provide to the visitors, customers. So another reason people are looking for positioning system is, for example, here we have some shoes, okay? So they may want to check, okay, for all these shoes, how many times the shoes has been taken up by the customers, okay? And more than that, how many times the customer really pick up the shoes, take it to somewhere, maybe in front of a mirror and try it, or they just pick it up, and then put it down immediately. Then they want to know this kind of information for marketing purpose about the design of the shoes. Maybe the shoes just put in the spot, which really attract the customers, but actually the design is not so nice. So that maybe a lot of customers pick up this one, but they immediately put it down. Then after we get this customer behavior, then people do a lot of data analysis, big data, blah, 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 these sort of things. Then they may find a better strategy, how to maybe swap the location of the shoes from time to time in order to increase the profit from the store. And of course, I think it is also very obvious that positioning system can help us to navigate in big museums, fine art exhibitions, interacting games using positioning system as well. And also for tourists, they may come to another place with another language, for example, don't speak French, then it will be very helpful if we have an indoor positioning system and like visit some museums. Okay, so there are many different technologies available. Maybe you also heard of some technology like Wi-Fi, Bluetooth, RFID has been used in a lot of airports. For example, for our baggage, maybe they put a tag on it, then they can trace our baggage in the transport inside the airport. And we will talk more about visible light method in this talk. But you can see that in different technology, we have different advantage and disadvantages. For example, in Wi-Fi, usually we are talking about the accuracy maybe up to 1 meter to 10 meter accuracy. So it depends. Some applications, maybe it is sufficient already. For example, in an airport, maybe if we have Wi-Fi positioning, then it can help us to find the gate. Maybe we need to go to gate 10, then 10 meter is sufficient. We already see the number already. But for some other applications, maybe like the one we talk about, the supermarket, if we want to locate the object, okay, and then we want to see the advertisement for certain product in our smartphone, then we really need to have something in the accuracy around 10 centimeters. Because if we are in front of this product, but it shows us the advertisement about something else, then it is not related, okay, maybe some other product. So it depends on application. So in general, the scale is like this. GPS, okay, maybe meter, the accuracy. Some other system, ultrasound, maybe centimeters level. And Wi-Fi, for example, we have accuracy up to meter. But not only accuracy, we also need to take care of the deployment cost, because we are talking about to make the engineering system be useful, then the cost cannot be too high. So some systems are very good. For example, the Wi-Fi, it has low cost because we can use the Wi-Fi signal. However, some other system, for example, the ultrasound one, maybe we need to install a lot of transmitter, then it will increase the cost. Of course, the coverage, we want to make it for the whole building, or in some applications, we just want to install it in a warehouse for some automation applications, then it is different. And the third one, the last one is about the privacy. So GPS, for example, is very good because the signal transmits from the satellite and the location is determined by the receiver. Okay, so this is one approach. Another completely different approach is, for example, the Wi-Fi one. Okay, the smartphone uses the Wi-Fi signal from different AP, then we see a different profile. And then it uploads to a server, and then the server determines where the receiver is. Okay? Then this server side determines the position. We may have some privacy concern. So for example, if I use my smartphone and use Wi-Fi positioning, then I may wonder, okay, then the system can track where I am. Okay? So some people may not like it, and also some applications we don't want to have. We have this privacy concern. We don't want the server side can check the user locations. So this is a summary of some system, and then summary of what we just talked about. So accuracy, privacy is one thing, and the cost is one thing. And cost, there are two kinds of costs. One is the equipment cost, how expensive the equipment is, and how much the receiver is, because we may need to deploy a lot of receivers for different objects. Another is the deployment cost. Usually it is about the labor cost. For example, is the system easy to be installed, or do we need to install a lot of infrastructure in the building in order to deploy the system? Okay, so by considering this concern, we have investigated the positioning system using visible light. And the basic idea is like this one, okay? So suppose we are inside a room, we have several LED on the ceiling, For example, maybe I replace all these lights by our LED light source, okay? Then we use our receiver, which has several multiple photodiode. So these are photodiode, or you call it photodetector or photosensor, okay? They are on a small pyramid, so they are pointing to slightly different direction, okay? And then we turn on the LED one by one. So say for example here, we turn on the LED for 2.5 milliseconds, very short period of time, and then switch it off. And then the second LED, and then the third LED, something like a TDMA, okay? We use the TDMA here. And then the fourth time slot, we just switch it off, okay? So, because the light is on and off so quick, so the human eyes cannot really see any difference comparing with a light source which is rather constant. So, for example, if we turn on this fluorescent tube light, they are also not perfectly on, okay? Usually there are some side wave depending on the power supply. Another example is our monitor. It is also flicking about 50 Hz, for example. So as long as the frequency is high, then the light is rather smooth and people will feel comfortable. So our receiver, we have different kind of receiver. Basically, we can make it smaller, but you know, in a university project, so usually this prototype bigger than what it can be, okay? So it is roughly 4 centimeters big by our final year project students. So this is the light intensity we measured by one photodetector, okay? So as we said before, the LED are on and off using the TDMA. So in this time slot, the LED 1 is on, and then this is LED 2, LED 3, and the fourth one is all the LEDs are off, okay? Then, for each time slot, as long as we use this one, this value minus this value, then we can tell the power we actually received by the LED 1, okay? So say for example, in this room, because the windows are open, mainly the windows, okay? Then this part may not be 0 exactly, maybe equal to 0.1 for example. Then everything will be shifted up due to the background light. So that's okay, as long as we measure the light intensity from LED 1 roughly equal to 0.9, then we minus the light intensity in here, then we can tell what is the actual power we received from LED 1. And then it is a commonly known path loss model for light source to a photodetector. That is, if the transmitted power is certain constant, okay, then the received power is proportional to the distance square, and then related to the cosine of the irradiant angle, okay? So in other words, if we are right under the LED, the power is larger. If we are far away, maybe certain angle 45 degrees, then the power is smaller. With this relation, the parameter n is depending on the LED type. And also, it depends on the incidence angle. If the photodiode is pointing to the light source, okay, then the angle is 0, and the received power is larger. But if the photodiode is pointing to other direction, then the received power will be slightly smaller, depending on this angle. So that's why we use our pyramid receiver. So if you remember our small receiver, which has several photodiodes pointing to different directions. So from the same light source, okay, the power hits to this point. But if we have one photodiode, we have certain value, okay? But now we have 4 photodiodes pointing to slightly different direction, so they will get different values here, okay? Not exactly the same, due to this part of the formula. It depends on the incidence angle. And then we find out a way to rewrite this formula in terms of a matrix form. Then everything can be simplified, and then we can find out a vector from the received power of the 4 photodiodes and also the angle of the 4 photodiodes alone. Then we can calculate a vector pointing from the receiver to the LED. Okay? So once we have one vector from the receiver to the LED, then we can just reverse the direction of this arrow from the free LED, okay? Then the intersecting point is where the receiver is, okay? Of course, we need to know the location of the LED, just like if we use the GPS system. We need to know beforehand where the satellites are, and then we can calculate where the receiver is, okay? So this is the rough idea of our algorithm. Is it okay? And then, of course, this is just the ideal case. Everything will intersect in the one point, but you know there are always noise in the system. So there are some error. This vector may be slightly changed to the direction due to the noise. Then we may come up with something like this. So we have solved an optimization problem to find out how to approximate the true position. Okay. So one picture summary of the system is like this. Okay. So we have light sources, we have our receiver. Different photodiode will receive different power from the same LED source. Okay. Then we calculate the vector pointing to the LEDs, and then after that we can find out the receiver position. So this is the whole idea. Okay, then we need to see whether this system is good or not. Then what is its performance? Okay, so we have tested our system in a small office. So this is our lab, okay, which is not too big. The good thing of this small lab is that because the light may be reflected by the wall, okay? So in the previous model, you see that we never consider this kind of reflection. We assume, okay, there is no other reflection, just background noise. Then we want to test it in an experiment to see how good or how bad it is if there are also reflections from the wall. And the experiment was done by one of our students. So he just hold the receiver and try to push it as fast as he can by moving his hand. So it is roughly 1.3 meters per second. And then we use a camera and make a video so that we know the true position at every moment when he moved the receiver. And then we compare with the estimated position from our system. Okay? Then we can see the difference. So you can see that the largest gap is here. So it is roughly, maybe it is very small. So it is 6.9 centimeters. Okay? And the average position error is within 10 centimeters. So this is the performance of our system. And also another important thing about the positioning system is, suppose this is our receiver, we need to know not only the X, Y, Z coordinate position. Another interesting thing is what is the orientation of the receiver. That is, we are holding the receiver pointing to this direction, or we are holding the system pointing to this direction. Because, for example, if we are in a museum, maybe I'm looking to this direction or looking to this direction is completely different. Or in a supermarket, we are looking at different product. So that's why we also want to know what is the orientation angle, comparing with the true angle. And we find out the average error is within 10 degrees. It is very accurate. Also about the cost. So the requirement here is need to replace the LED light. Okay. So yeah, this is the main cost. But the good news is that we don't need to put all the wires, etc. We just need to replace the light. Okay. And also, you know, LED light, the price is dropping. It is getting cheaper and cheaper. So it is good technology, and we expect the cost is reducing. And also, it can help the client, for example, they can save electricity. So eventually, they will save this money back for buying by replacing the LED. And also, you know, LED lights can last very long. The expected life can be over 5 years, up to 10 years. So another properties of our system is that it uses visible light. So visible lights we use almost every room, right? So the good thing is that it doesn't introduce extra EM wave. So for example, if we are very scared of bandwidth for data communications, okay, we don't want to put another system here and waste some resources for positioning. Because we use visible light, it won't interfere with other communication systems like using Wi-Fi or Bluetooth, etc. Okay. And also, the principle is a bit similar to GPS. The position is calculated at the receiver side, so no server and no privacy concern. We don't need to worry too much. The server side can track our position because they never know. So there are some other, of course, there are some other research groups have done this kind of research using visible light to do positioning. But our new stuff is that our algorithm is different. So we can remove some of their assumptions. For example, some existing paper may talk about the receiver has to be at a fixed height, or the receiver has to be always pointing upward. But we don't have this problem because actually we also use an IMU, inertial motion unit, that is the accelerometer inside our receiver in our calculation. So no matter the receiver is horizontal or inclined, we can still calculate where it is. And yeah, so there are some other properties, and I think I will skip here. But of course, due to the limited time, I just talk about the indoor positioning here in the first part. For visible light communications, there are many other applications. And we have also done something about communications and also security applications. Just a very quick example. For example, if we use light as a source to transmit information, then you can expect that if we are in a room with all the windows shuttered or closed the door, then the signal you transmit here cannot penetrate the wall, and the guy next on the next door or next room, they cannot receive the signal. So comparing with Wi-Fi or Bluetooth, this EM wave may go everywhere unless you do something special to protect your room. So this is one of the benefits of visible light communications for both security reason and also the frequency reuse reason. Okay, so every room you can reuse the same frequency because it won't interfere the others. Okay, so for the rest of the talk, I will quickly talk about something about our latest result. Okay, so one of the important problems in this positioning system or communications is to do channel estimation. So channel estimation is an important problem because if we have a good estimate of the channel gain, then you can have better data transmission rate. And also in our positioning system, we need to use the channel gain in order to determine the position. So it will determine the accuracy of our positioning system. And also it can improve the sequence key rate we can generate in the system. So the question is, how can we do a good channel estimation in VLC system? Okay, so this is the second part of our talk. We are going to look at this. And maybe you may wonder, okay, channel estimation is a very old problem, right? It should have been done, well investigated in radio frequency. Then can we simply borrow all the ideas from the radio frequency which we use nowadays in VLC system? So the answer is no, there are something different. So that's why a lot of people have investigated in this problem and also including our group. Maybe let me directly jump into the property of VLC system and then I can tell you why they are different. So VLC system, reduced light source, photo detector. So it is, some people call it phase-space optical communications. In this case, we usually use the intensity modulation, the light power, and also the direct detection and the receiver. In other words, both the transmitted signal and the channel gain are non-negative real numbers. Okay? So very different from radio frequency signal, we model them by a complex number because it has phase and also maybe a sine wave, something like this. But here, they are modeled as just a real number, positive. And another important property is that we cannot forget that at the end it is still for illumination. We don't want to impose this system and then every time it is very dark. We want to maintain the same light intensity. So the light intensity is a requirement here. So that in a radio frequency system, maybe we want to save energy for the channel estimation part. But here, instead, we want to make sure that the transmitted power is at a certain level. It cannot be too small. Otherwise, it will be too dim for the system. On the other hand, it cannot be too big as well. Okay? And also the light sources, because it is positive wave, so it is larger than or equal to 0. But it has a maximum power constraint. Because, for example, if we buy an LED 10 watt, for example, then the maximum power is 10. We don't want this number to be too big as well, because then we need to buy an expensive LED. So these are the power constraints we have. And it is quite different from the old results for radio frequency systems. What we need to do is to design a pilot design, and then it is modeled by a matrix A, and then these pilot sequences, okay, we put it in each row. For the ith row is for the LED I, and then these pilot sequences will be transmitted by the LED to help us to estimate the channel gain. So I follow the previous example, but here I have 4 LED. Okay, so I let, for example, V equal to 4, we have 4 LEDs, and then we transmit the light. And also because, remember, the light pulse is on and off very quickly. We are talking about just milliseconds. If we move maybe normal speed, walking speed, then the distance within 10 milliseconds is still very small. So the channel gain is roughly the same in this period of time, so that we just assume it is a constant. And what the receiver receives is the channel gain multiplied with the LED power, and then the superposition of the all LED signal, and then added with the Gaussian noise. Okay. And here we follow the literature. We assume the noise is Gaussian noise independent, so that's the problem is tractable. And then we will use a linear estimator at the receiver in order to estimate the channel gain. We multiply the W with the received signal Y. So, because the receiver is usually under the light, then the direct line of sight is usually assumed. We assume the receiver can see the light sources. So that if we don't use the zero forcing receiver, then we will have trouble. Because if we estimate the channel gain, okay, if we have the true channel gain together with the interference power, then this one will dominate the noise. Okay? So that's why we usually consider the zero forcing estimator. That is, when we multiply the estimator to the received signal, we have only the true channel gain together with the noise, okay, multiplied with the W, instead of the contribution from other LED lights. Okay? This is important because, for example, if we look at the positioning applications, the position result is a function of the estimated channel gain. So if we have some other power from other LEDs here, it means that no matter how long our pilot sequence is, that is, okay, maybe I can spend 1 second to estimate the channel gain. I want to make it very accurate. If you have another term here, this one will never converge to the true channel gain. Okay? So that's why we want to make sure, okay, we are considering a receiver, the estimator will give us the channel gain together with a noise. The noise term will go to 0 as long as we make the pilot sequence long enough. Then we will converge to the true position. So this is the idea of the system. That's why we consider a zero forcing estimator. And then we use the capital W to denote the estimator. So one of our previous results is that we find out for any pilot sequence, for any pilot scheme, the best estimator we should use is the pseudo-inverse. That is, if our pilot sequence is A, the capital A, we have a set of pilot sequence, the best estimator we should choose is to consider the pseudo-inverse of A. The best means that then it will minimize the noise variance which we have seen in the previous slide. That is this part. We want to minimize this part. Then this one, the variance will be smaller. So now, if we know that the best choice of the estimator is the pseudo-inverse, then we just need to plug in this choice of W into this formula. Then we can write down the noise of our system in terms of our choice of pilot sequence. Okay? So if our choice is A, then the noise of our system is just the A multiplied with A transpose inverse, and then take the trace. So that the problem is very clear now, is that suppose we have a pilot design which is suitable for the maximum power equal to mu, the average power equal to phi, and we have V LED, and the pilot length we can accept is length B. Then we want to know among all these pilot designs, which one can give us the smallest noise. Okay, so this is the problem we want to deal with. And of course, we also want to know what is the lower bound on this value. That is the fundamental limit, what we can do, what is the best we can do, and then we try to find out the solution. Okay? So this problem, it happens to be tractable. Okay? We can find out a tight bound, that is this bound. We can find out some cases, some conditions, as long as you satisfy, then there are some scheme which can achieve this bound. So that this is a tight bound. Okay? And also this condition will be very useful when we want to find out the optimal scheme. This is we are going to see. Okay? And here we can look at these conditions when the bound will become tight. Okay? Because this will give us some insight. So it tells us that the optimal choice of the pilot sequence should have the following properties. The first one, the power on each LED should be the same, okay, for the optimal choice of the pilot sequence. This part, it tells us that the correlation of any two pilot sequence should be the same, okay? If you take any two, you calculate the correlation, they're the same. This condition tells us that for the best scheme, the total power emitted by all the transmitter at every instant, it should be the same. Okay? And then the last one, it tells us that for the best choice of sequence, we should always make the LED either completely off or turn it to the full power, except for one time slot. Maybe we use something in the middle in order to satisfy the average power constraint. So this is a very nice properties because we consider a problem that the LED source have a freedom to choose any value, any real value between 0 up to mu. For example, mu is 10 watts, then it is a real line. Okay, 0, 1 watt, 2 watt, 1.3 watt, or 9.9 watt we can also use. Okay. Then there are many infinite number of choices. But the condition here tells us that, okay, it is not so complicated. The best one is either you switch it off or turn it on, okay, full power, except for one time slot. Then it can simplify the problem a lot. And especially you see that the upgrade part of this formula is due to this term here, okay? So as long as if we consider a problem that the average power multiplied with the length, this is the pilot sequence length, if it happens to be an integer, then everything can be simplified to a much nicer form, okay? So this is just the previous bound, but we consider this guy is an integer. And also the last condition become cleaner, okay? So every time slot, either off or full power for the LED. So this is the insight we can get from this bound about the optimal design of the estimate for the pilot sequence. And here, this is the plot for the two bounds we have obtained. So we expect that all the scheme should have noise variance about this blue curve, okay? And this example is, this is the maximum power for LED, pilot sequence equal to length equal to 8, and we consider different average power. So this is the region we can characterize, and this is the fundamental bound. And of course, if we consider phi, it happens that certain value, 3.75, for example, we multiply with the length equal to an integer, then these two bounds will touch each other. Okay? And the optimal one, you see that it is along a very nice curve, very funny. Some concave function, okay, on a convex curve, okay. But for the bottom one, the simple one, we can prove that it is a convex function, okay. And another interesting observation here is that we find out the optimal average power, okay, is not 0.5, but somewhere near to 1/2. So it means that for the optimal design, we usually like the light source to give out the average of its maximal power, roughly 3.5 something. Okay, so I think we have, how much time do we have?
I think we can end at 55. We can just like break like 2 or 3 minutes.
Okay.
We can 7 or 8 minutes.
Okay, then I want to tell you another thing immediately, maybe, because I don't know. This is something that for coding guide, for coding theory, people have used it a lot. So I'm not sure if any audience here may use a lot of coding theory. So I want to tell you this part. Okay. So far we have talked about the bound, right? And the conditions when we can achieve the bound. That is when we can get the optimal code. Of course, we want to know, tell me exactly how to design the system so that it is the best. So this is the scheme, okay? Can tell us how to design the optimal scheme, okay? So this is theory borrowed from coding theory. It is called a balanced and complete block design, okay? So this is a mathematical structure that we consider a pair, V and B. It is called a BIBD. If it satisfies the following constraint, okay? So let me use this example to explain to you, it will be easier. Now suppose we start with a set V, okay? So for this V, it has 1, 2 up to V elements, or we call it points, okay? So for example here, V has 1, 2, 3, 4 points, okay? And we consider a bunch of sets, okay? B1, B2, they consider a subset of V, okay? So say for example here, B1 contain 1, 2, B2 contain 1, 3, B3 contain 1, 4. They are all taken from the set V, okay? So one requirement to be a BIBD is that all these sets has the same size. You see here, they have 2 elements only, okay? So that's the parameter K here is equal to 2, okay? So another requirement here is that every pair of points contain an exactly lambda of blocks. So say for example, I just randomly think of a pair of number, 2, 3 for example. Then you check here, 2, 3 only here in the block 4, okay, just one block. And maybe we consider another pair, 1, 2 for example. 1, 2 is here, it contains only in one block. So you can name any pair, okay? We will find that it is always in only one block. So that in this case, lambda is equal to 1. And if you satisfy these two properties, together we let B equal to how many blocks here, then this is called BIBD. Okay? This is the balanced structure, the number of points and the number of pairs in how many blocks. And of course, except this form, we can also present this relation in a matrix form. So here you see that I purposely put 1, 1, 0, 0 here because the set B1 has only point 1, 2, okay? So that I put 1, 1 here, 0, 0 here. Or if you look at the last one, B6, because it has 3, 4. So that we put 0, 0 here and 1, 1 here, because 1, 2, 3, 4, okay? And it is the same for the other columns. This is how we construct this matrix, and it has a name. It is called the incidence matrix of a BIBD. So the answer of the previous thing I promised is there is a one-to-one correspondence between BIBD and the optimal design of a pilot sequence in VLC system. That is, for any incidence matrix, okay, it is an optimal pilot design for a certain VLC system. And the correlation, you remember these are the power constraint, number of LED, and the pilot sequence length. And here is the VK lambda we just talked about for BIBD. As long as these two formulas are satisfied, then this one-to-one correspondence will hold. Okay? So in other words, because there are lots of resources about BIBD, a lot of people have done research about this, below a list of BIBD. So as long as we are given a BIBD, we can find the corresponding optimal pilot sequence for VLC system. Now let's do an exercise. Okay. Now suppose we consider the maximum power equal to 1, average power equal to 3/7, and we have 7 LEDs. The pilot sequence length doesn't really matter. Okay, we make it any value, we accept it. Then what is the best pilot design? Okay. So the pilot sequence length here, of course, it has certain meaning. It is called the latency constraint, because if the pilot sequence is longer, it means that the receiver needs to wait longer before it can do the estimation. So one of our previous results, we have a way to find out optimal design, and the length is equal to 35. Okay. But if we use a BIBD, one of the BIBD we can find in the literature is called 731 BIBD, and it is the incidence matrix of this is a 7 × 7 matrix. In other words, it is a bunch of pilot sequences with length equal to 7. Okay, so it is a much shorter. And of course, for this matrix, we can concatenate them. That is, we put one matrix here, and then we put another matrix after this. Then it is, in other words, just like this one. Okay. Suppose you have a matrix, you can put two matrices together, so you can have a new pilot sequence with 6 elements. Suppose originally you have 3. Okay. Then we can do the same. If now we have a matrix from BIBD, we can just concatenate them. Then originally we have a length equal to 7. Then we can have a new design with 14 elements, or another pilot design with 28 length equal to 28, or length equal to 35. In fact, for this result, we will rediscover our previous one. They match with each other, exactly the same thing. Okay. But one thing I want to clarify, make sure don't misunderstand, is that here, as long as we make the pilot sequence longer, the noise variance will decrease. Okay, so this one will have a larger noise variance. But the good thing is that it has a shorter latency. Okay, here we spend more time to do estimation, then the result is more accurate. But of course we need to wait longer. So this is the trade-off. But all these designs are the optimal with respect to this length. That is, you cannot find another design with length equal to 21 but better than the performance using the BIBD 3 times. Okay, so this is the message. Okay, so there are some simulation results, experimental results, but I think, yeah, you expect that I must say that, yeah, using this code is better. So I think we can skip this. And yeah, we also recently expand these results to include the case that there are some background lights as well, and it is also applicable. Okay, so to conclude this talk, so yeah, actually we have just talked about a small part of what we have done, and also if you know VLC, there are many other groups that are talking about different applications. So communication, securities are also very hot research topics. And here, for the second part, we focus on the channel estimation because our group mainly focused on communications and positioning. And we have seen that there is a fundamental bound on the total noise variance, and there are some sufficient and necessary conditions for the bound to hold. So these conditions give us insight on how to design the optimal system. And here, we can see that this system is different from the conventional radio frequency system. We want to make sure the transmitted power is sufficiently large, because we also use it for illumination, for the lights to be strong enough. So that, so there are some new research problems comparing with the conventional estimation problem. And we have seen that using BIPD can tell us how to find the optimal pilot design. And so that's it. And thank you for your attention.
Probably we have time to allow a few questions, either on the theoretical, fundamental result, or experimental, or applications. Please feel free if any question relate from the application or from the theory where you did a hardware and software design as well.
So the question regards the practical implementation of the system. So your assumption is that you have always your visible light comes to your device anyway. But in practical situations, this is not true. So you need to have more light sources, and in this case, does the formulation from where you take the optimal sequence change?
Yeah, so here, this one is just for the case that are offsite. But you can see that, for example, if I just hold the receiver here, it is quite likely to many light sources, it is within offsite.
It depends if the sources are here, yes, but if they are behind you, not.
Yeah, so, but I mean, in practice, we tried it in a room, for example, it is quite common. Because one thing is that because it is for illumination as well, for the light sources. So when we decide the location of these light sources, we already make sure that maybe someone will write something or read something. You want to make sure that the human body won't block the light. So that's
all of their sources.
Yeah, So yes, so you worry about the low light sources. So for example, if we do positioning, we just need to see 2 light sources.
Okay.
Yeah, then we can do positioning. So we don't need to see all.
And the result of the optimal sequence holds also in case only 2 out of 3 is.
So it doesn't really matter. Okay. So this means that maybe some other light sources you consider as 0 if it is for the power. Then of course we cannot estimate the channel gain. Okay. But if you want to do positioning, then we can still, for example, maybe I stand like this. Okay. I cannot see the light from this one. But maybe just these 2 will be sufficient for me to find out the position. Or for communications, okay, then I don't use this transmitter, I use these 2, okay?
Implementation-wise, what are the sizes of matrices that you deal with, what are the kind of processing constraints in the positioning, for instance?
Oh, because, so let me see, the largest system we have tried to be 5 LEDs, so it is, I mean, the longest you can take 5 and it's sufficient. Yeah.
5
yeah. But I think we have tried it. We have tried it. Let me see. For the experiment. I think we have also tried it this one. Yeah. Yeah. But yeah, because everything is just a matrix multiplication, so we won't take too much time.
So you use like microcontrollers?
Yeah, Arduino. Arduino.
Just coming back to the first question, I'm sure that there are plenty of use cases for which your results are very interesting. I'm not sure that the case of the shoes is a very good one, or a supermarket in general. Because on the first hand, when you go to take shoes, you never put them back in the same position, right?
Yeah.
And if you put the device in front of the wall, you're done. But in a supermarket, in addition, you have a row of products. So you're going to see only the first one, and you know how people do things. They mix up everything.
Yeah.
So the issue that you need to have a direct, how do you call it, a direct vision between I think it's a big limitation for this type of solution.
Yeah, so it depends on application. For example, if we talk about supermarkets, maybe this one. Then what I expect is that we are not locating the objects here, okay? We are locating our smartphones, for example. So maybe this is my phone, okay? So I point to here, then I can see, okay, this product, some information. Maybe, yeah, every details on the box I can see in my phone, okay? So when I move my phone, then I will see something else, yeah. Because we won't put the receiver on the product, it may cost too much. But for the shoes, yeah, actually we have some collaboration with a local company in Australia. We made a prototype for the shoes. Then it has a larger space. We can put all the hardware here inside, and then we put the receiver on the top of this part. Okay. Then, yeah, just like what you said, they also say that they wanted to see whether the shoes has been misplaced somewhere, then they can check. Yeah.
But in general, another question is, if you come back to the supermarket issue, the trend is to introduce augmented reality in the supermarkets to do these type of things.
Yeah.
So how do you compare your solution with the augmented reality one? Because in the augmented reality, if you're looking for some good, the good will flash or something and will directly tell you exactly what the product is about.
Yeah, so this technology should use together with virtual reality, those technology. So this one will only provide the location information.
No, I got it.
Yeah, then we need some other people implement the virtual reality thing, maybe on the smartphone, then to help us to make the things more interesting.
Yeah, no, my point was just that if you think about the supermarket making an investment in order to digitalize the market, I'm not sure if they will go into intermediate phases or if they go move directly to a more sophisticated solution like the Amazon Go or whatever.
Yeah, so for the supermarkets, I think to provide this user experience, then they will just increase their cost. But for themselves, they may want to know the user's behavior. Maybe the heat map in a supermarket, which parts the supermarket has been exported by more customers, then this information may be more useful for them. Yeah.
Maybe we will stop right now to have the second part. Okay, sorry for the very short transition. Okay. So thanks for